SwayamPrabha. Digital India. Educated India.
Now we are going to start one of the most important topic in this course, which is basically how we can design the flight control system in linear regime. First, we'll come up with the list of equations, which involves the rotational dynamics and translational motion of the aircraft, followed by the kinematics. Then we'll divide the equation into two sets. One set will be representing the longitudinal motion, another set will be representing the lateral directional motion of the aircraft. We'll see the equations will be highly complex and nonlinear, but to design the linear controls, we should have the linear form of the respective equations of motion. Here we're going to use the small partition theory and how we can come up with the linear state space model of the respective equation. We'll discuss them in detail. Then we'll start what are the different modes are there in the longitudinal motions and lateral motions. We'll discuss in detail. Basically, what are the approximation in the different motions. Here we're gonna go for more than 7-8 lectures in this direction, in this content. Hello everyone. Here we are going to start the second part in this course, the equation motion of the aircraft and how we can design the control for the same. So here we are going to consider the longitudinal motion of the aircraft and the lateral motion of the aircraft and how we can come up the linear model of these equations, and also what are the different modes are there in the respective equation motion, the longitudinal motion and lateral motion. So let's start with the equation motion of the aircraft. Equation of motion of the aircraft. So here we are not going to go the details how the equation being derived. We'll write the final form, and from those equations we'll come up with the lateral motion and longitudinal motion, and we'll go to the linearization technique and how we can come up the linear model of the respective systems or equations, and we can design the control. So let me write the note, then we can write the equation of motion. The rigid body equations of motion are obtained from Newton's second law, which states that the summation of all external forces acting on a body is equal to the time rate of change of the momentum of the body. So this talk about the forces equation, and if you consider the angular momentum equation and the summation of the external moments moment of momentum, or we can say angular momentum, the time rates of the change of linear and angular momentum are refer to the absolute or inertial reference frame. For many problems, in airplane dynamics, an axis system fixed to the earth can be considered as an inertial reference frame. Let's consider the following figure where all the forces, moment, and axis system are defined. So let's consider we have aircraft model. The aircraft model, and let's assume the CG of the aircraft, and this is the x-axis, and this is y-axis, and this is z-axis. And the body axis along this is the body axis, xp, let's assume, and this is yb, and this is zb, and the total force along x-axis, the aerodynamic and propulsive force we are assuming along x-axis x, capital X, along y-axis capital Y, and along z is capital Z. And the rates along x-axis, let's assume this is P, along this Q, along this R, and the linear velocity along x-axis we are assuming U, along y is V, and along G is W. And let's assume this is the total velocity of the aircraft, which is along this line, and we are assuming this is capital V. So now let's define what are the terms being used here. Let me write those things. So here capital V is total velocity of the aircraft. And U, aircraft translational velocity in the XP axis. And V, aircraft translational velocity along YB axis. And W, aircraft translational velocity along ZB axis. And let's assume P with the aircraft roll rate about XP axis, and Q, aircraft pitch rate about YB axis, and R, aircraft yaw rate about ZB axis. And L, okay, another part I have missed here. Also, let's assume the moment along XP is L, moment along YB is M, and moment along ZB is N. We are assuming. So here we can write L, aircraft rolling moment about XP axis, and M, aircraft pitching moment about YB axis, and N, aircraft yawing moment about ZB axis. And this capital X and capital Y, capital G with the aerodynamic and propulsive forces in XB, YB, and ZB axis respectively. Right. So we are assuming X, Y, and Z with the aerodynamic and propulsive forces. So these are in the aircraft we are generating, but also we are having the gravity force also acting in the aircraft. So let Fx, Fy, and Fg be the total forces including gravitational force components along X, Y, and Z body axis. This will X be body axis. Then we can write the force equation. Then the force equation we can write Fx equal to m into u dot plus qv qw minus rv, and fy m into v dot plus ru minus pw, and fg equal to m into w dot plus pv minus qu. So here m is the total mass of the aircraft. I'm not going through details how this equation are come. So this is basically force equation, we can say. Force equation. Here, basically, I write. So here, fx, fy, and fz constitute the x, y, z aerodynamic and propulsive forces and gravitational force component. So we can write here fx equal, we can write x plus, so along x direction total force is fx, which constitute the force along x-axis due to the aerodynamic and propulsive forces and fx gravity forces. Similarly, fy you can write y plus fy gravity, and fc we can write z plus fz gravity forces. Now the gravity forces along the body axis are found to be fx gravity equal to mg sin theta, and fy gravity equal to mg cos theta sin phi, and fc gravity equal to mg cos theta cos phi. So here theta phi psi basically is roll and psi angle. Now if you combine all the force term to this equation, if you substitute fx, fy, fz in equation force equation, so we'll have the force equation, becomes, we can write x minus mg sin theta equal to m into u dot plus qw minus rv, and y plus mg. So this should be negative mg gravity, this should be negative here, mg sine theta, and mg cos theta sine phi equal to m into v dot plus ru minus pw, and along z, g plus mg cos theta cos phi equal to m into w dot plus pv minus q. So this is the complete force equation for the aircraft. Now we'll write the rotational motion of the aircraft. This is already have written the rotational motion, but let me rewrite the equations for rotational motion. Basically, in the first part of this course, we have designed the classical control for the rotational motion of the aircraft, how we can control the angle of the aircraft. Rotational motion of an aircraft can be written as L, total moment acting along x-axis, equal to P dot Ixx minus R dot Ixg Qr Igg Iyy minus PQ Ixg, and M equal to Q dot Iyy plus PR Ixx minus Izzz plus Ixz P square minus R square, and N equal to minus P dot Ixz plus R dot Izz plus PQ Iyy minus Ixx Qr Ixz. The rotational kinematics, this is the rotational, this is the moment equation. And if you write the kinematics equation and the rotational kinematic equation can be written as phi dot equal to P plus Q sine phi tan theta plus R cos phi tan theta dot equal to Q cos phi minus R sin phi psi dot equal to Q sec theta sin phi plus R sec theta cos phi. So this is the rotational kinematic equation. So for ease of the motion, we can denote for the ease of the motion, we denote I x x, I y y, and I g g by I x, I y, and I z. Another important condition we should write here. What is the condition for the steady trim condition? Because this will be kind of reference point for finding the linear system. For steady state trim condition, or we can say this is basically, we can say also equilibrium point or equilibrium point during level flight. The following condition must be satisfied. So this is the condition required to finding the linear system. V equal to 0. So it means side velocity is 0. This is the first condition. And phi equal to 0, the wings level. This is basically wings level. And so it is, there is no state, basically wings are balanced with things, and P, Q, and R equal to 0. So we are assuming the 0 angular velocity. So these are the conditions needs to be satisfied for trim or steady level flight. Now we'll distinguish for the what are the equations are involved for the longitudinal equation motion, and what are the equations are involved for the lateral equation motion. So the longitudinal equation of motion defined by the following set of equations. What are these? X, the force along x, mg sine theta, m u dot plus uw minus rv, and which consider the force along x-axis and z-axis. So the equation will be, assuming for longitudinal motion are the equation along force equation along x-axis, force equation along z-axis, and the moment equation along y-axis, we are assuming. So x g plus mg cos theta cos phi equal to m into w dot plus pv minus u. And we'll assume moment equation along y-axis. So m equal to u dot I y plus pr ix minus iz plus p square minus r square into ixz. So these are the equation involved for the longitudinal motion of the aircraft. And we'll see what are the equation involved for the lateral directional motion. So the lateral directional equation So we generally call lateral and direction together. Lateral directional equations of motion can be written as, so force along the y-axis, which is force equation along y-axis, y plus mg cos theta sin phi equal to m v dot plus ru minus pw, and moment along x and g. So we are assuming L equal to P dot Ix R dot Ixg plus QR Ig minus Iy minus Ixg PQ, and N equal to minus P dot Ixg plus R dot Ig plus PQ Iy minus Ixg QR. So these are the different equation of motion, and first we'll start with the longitudinal equation of motion, and we'll find the linear model of the longitudinal motion using the perturbation theory. And once the system is a linear model, we can design the contour easily, because we are in this course mainly we are discussing about the linear contours. Then we'll start with the lateral directional motion equation, and also we'll be using the small perturbation theory here, and we'll find the linear model of the lateral directional motion, and we can design the linear contour. So let's stop it here. From the next lecture, we'll be continuing how we can come up the linear model of the longitudinal motion using the perturbation theory.